the first step to solve any thermodynamic system is to define that system. Define that system with a drawing. We have to see where the system is, what is a part of the system, what is part of the surroundings, and separate that with a boundary. So systems and control volumes are the first step in solving a thermodynamics problem. You have to define the boundary. System, surroundings, and boundary. Always. System, surrounding, and boundaries. What is a system? A system is the quantity of matter or region in space chosen for you to study. The mass or the region outside of that system is called the surroundings. The real or imaginary surface that separates the system from its surroundings is called the boundary. The boundary can be fixed or the boundary might move. Some mass transfers over the boundary. Sometimes mass doesn't transfer over the boundary. But the boundary contains no mass, and it does not occupy any volume in space. Systems can be considered closed, or systems can be considered open, depending on what you define as your system and its surroundings, and depending on whether a fixed mass is inside it or a fixed volume is chosen. They can also be, they can also have flow into and out of the boundaries or no flow. So these are the types of systems we can solve in thermodynamics. We can have systems that have flow going into and out of the boundary. We can have systems where the whole problem has a fluid inside a boundary where nothing flows in or out. We can have closed systems or we can have open systems. So that's all fine and good to say, but what does it actually mean? So what does this look like in practicality? Well, let's draw a few things. If we say that this is you know, this we're doing applications here. We're not just talking about a thermodynamics textbook. We want to talk about the real world. How does this apply to the real world? Well, let me draw a few systems that occur in the real world. What I'm drawing here is a heat exchanger. It's sort of a stylized drawing of some tubing, but the volume is not changing. Heat exchanger. And that heat exchanger, as you know, can be a evaporator or a condenser, depending on which way the heat is going to be traveling. Let me draw another familiar system. This familiar system has a piston in a cylinder. So this is a familiar system that is a reciprocating cylinder. And so this is reciprocating cylinder. Another system that we know, some of us know, some of us don't, but we'll know, is that of a turbo machine. This is a turbo machine. It could be turbocharger, a supercharger, some sort of a like a turbine. So I'll call this a turbo machine. And then I'm going to draw this thing. It's just something that goes from volume to another volume where the second volume is greater than the first volume. And this would be commonly called, if this is a cross section, this is commonly called a nozzle. So here are some common applications of thermodynamics. Okay, so what we have to remember is the first step in solving a thermodynamics problem is the description of a system and its boundaries. Boundary. And a person said that, a scientist named J.H. Keenan, not so long ago, 1941, around, I don't know, your parents' or grandparents' time. My parents' time, maybe your grandparents' time. So I showed you these common applications of thermodynamics down here, and Keenan says the first step in solving a thermodynamics problem is to draw out the system and its boundary. So I'm going to draw the boundary in, let's do it in this fuchsia color. So if I were to look at this boundary of a heat exchanger, I know that mass is flowing into one side. So, but I have to have a distinct amount of volume to study. So I'm going to close off that side wherever I want to. I could have closed it over here, but I decided to close it at the end. Of course, my calculations depend on where I closed it, but my calculations all start with the definition of that boundary. I'm going to include all the volume inside this tube as part of my system. If it's called my system, then it's inside my boundaries. So I better draw a boundary around all the fluid that's inside this tube. Here we go. I'm drawing both sides here. Could have made this picture a bit bigger. Drawing both sides here. And what I'm trying to visualize is that my system is what's inside these tubes. So my system is in there. System. And my surroundings are out here. Here are my surroundings out here. All right, make this a little bit bigger. My system and my surroundings. And what this pink part here is the boundary. In the case that I just drew here, in this case that I just drew, I do have mass flowing because this is just a heat exchanger is just part of a system. So typically I would have some mass coming in, some mass coming in the form of a fluid, maybe a liquid or a gas, and the same amount of mass is going to come out. And I know it's the same amount of mass because it had nowhere else to go. When we denote something that is flowing, we denote it with a dot over it. So this is the mass flow in, and this is the mass flow out. And the same amount of mass is going to flow in and out because it goes nowhere else. And another thing to note here is that there is a volume at the beginning and there's a volume at the end. And in this case, volume 1 does equal volume 2 in this system because I don't see anything compressing this. And you might have a problem visualizing that. If you do have a problem visualizing that volume hasn't changed, take a look at sort of a cylinder here, and then a cylinder of the same length here would be the same volume. A cylinder of the same length here would be the same volume. A cylinder of the same length here would be the same volume. So as this little volume works its way through, you see it's not changing. Whereas in the case of this nozzle, of course, it would be changing considerably, right? So very different thing. All right, so that's a system of a heat exchanger as a practical thermodynamic system. That's how you define the boundary. the system and the surroundings. Very, very important first step. And then all we have to do now is apply our calculations to it. So let's look at the next system. The next system is a reciprocating cylinder, or as you might call it, a piston. In this system, I'm going to be really concerned with the fluid that is being compressed. It compresses and it expands, it compresses and it expands. Here, I have no mass flowing through the system. The same amount of mass sits in there. It gets squeezed to a smaller volume, and then it gets opened to a bigger volume, and nothing is moving across the boundaries. Now, I could make a system where some fluid comes in and then goes out again, but that's not what I drew there. So what I drew here is a closed system, but here it is an open system that I drew with a heat exchanger. This is simply a closed system. I don't have much else to say about this other than this is the system. The system is a fluid that's in here, and this is the surroundings. And you can imagine the ideal gas law, PV equals nRT, happening inside here. Let's look at the next practical machine. The next practical machine is a turbo machine. I have some options. I could put the system way over here, but I don't want to. I can make it wherever I want, and you can make it wherever you want. But then your math just has to be consistent with what you've made. And that is up to you to do. I like to take the system of a turbo machine as being the circle just around the outside of these turbine blades. I like to look at that. I think that's a practical system to look at. And then out here is the surroundings. And what I notice here is that there's an inlet. There's an inlet and there's an outlet. So because there's an inlet and an outlet, I can assume that there's going to be some flow in and some flow out. And it's not going anywhere else, so it's probably the same flow in and the same flow out, but there might be some losses. Because there's flow in and out, I would call this an open system. Open systems have mass flowing through that boundary. And our final example is a nozzle. In the case of the nozzle, I have some fluid coming in and I have some fluid going out. I don't see it going anywhere else, so it'll have the same mass. I can tell it definitely doesn't have the same volume, though. Definitely doesn't have the same volume. But here we go. If I were to define a system here or a boundary, I would make it look like this. You can do different things if you want to. This is my boundary. And this is my system. And these are my surroundings. It looks like mass is flowing in from the surroundings into the system, and then mass again is flowing out of the system, doing work on the surroundings. The volume at the outlet is bigger than the volume at the inlet, hence it is a nozzle. And I would call this an open system. So here we go. We have demonstrated the first step in solving a thermodynamics problem, which is to define the system, the surroundings, and the boundary. And we have applied that to 4 common types of thermodynamics analysis problems that are practical, one being the heat exchanger, one being a reciprocating cylinder, one being a turbo machine, and one being a nozzle.